All right, so it's my pleasure today to talk with you about why I think soft sensors need structure and why we need soft sensors. I also have the pleasure of being one of a few soft roboticists or people working in the soft robotics world that is talking in this session, so I won't belabor the point about why we need soft robotics too much. I want to give two concrete examples of some things you can do with a good soft sensor. And when I say soft sensor, I mean a sensor that is made out of a soft material. So think rubber, cloth, sometimes paper, so really soft, flexible materials. So kind of spanning the gamut. On one side, we can think about health conditions, so wearable sensors that we're going to put on someone's body in a piece of clothing or similar, where we could do something with this sensor like monitor and treat fluid retention that is kind of an adjunct to a lot of different health conditions, heart failure, edema-related diseases, etc. The other, on the total opposite spectrum of soft sensor applications, is enabling something like a soft morphing bio-inspired robot. A researcher at Yale University, Rebecca Kramer Botelho, has this really cool robot where she has it has the ability to morph from a flat flipper-like leg to a round leg to be able to have both sea turtle and land tortoise types of locomotion. And so you might think about the fact that we would need sensors to enable both the locomotion across land, walking across land, as well as to understand that morphing state. All right, so the reason we need soft sensors is I kind of illustrated in the last slide is because the rigid ones are not great at soft interfaces. If you think about wearing a sensor yourself, maybe you've got something like an Apple Watch or a Fitbit. So those go in things like watch bands, but we don't yet have things that can be integrated into clothing reliably and measure other things that we might want to know about our bodies or ourselves. So soft sensors need structure because they're kind of deformable everywhere. So this is a problem in sensing known as being selective. I'll show you a quick video. So this is a sensor fabricated in my lab. It is a soft, stretchable capacitor. If you want to envision how soft and stretchable this is, if you or one of your kids or a neighbor kid or something has gotten one of those little sticky hands from the grocery store toy vending things at the front of the grocery stores, it's that sort of similar soft, stretchy material, softer and more stretchable than a rubber band. And so what I'd like to draw your attention to in this capacitor is that it's changing because my finger is tapping it, so it's responding to how the capacitor itself is being deformed. But it can sense pressure, it can sense if I stretch it, it can sense if I twist it. And so it's not selective. It can't tell me if I'm applying a pressure versus if I'm applying a curvature. When we think about putting these sensors on robots or putting these sensors on people, we do want them to be selective so that we can understand the difference between, for example, someone's arm size changing because they're retaining additional fluid versus someone's arm size changing because they went and picked up a heavy grocery bag and now their muscles have deformed in size. So we could change the sensor approach in a couple of different ways. So let's take one of the most commonly used sensor materials, which is conductive silicone rubber, conductive PDMS, with a bunch of conductive particles embedded in it. And so if we go and we strain this material, what we get is a change in resistance. It increases in resistance as those particles get further away from each other. And that relationship is captured by this equation. So I'm not going to go through all the parts of the equation. What I do want to highlight is the things we have control over with this, how sensitive this sensor is linked to its material properties. So what this means largely is if you want different properties for this sensor, you have to change the materials. That's about all you have control over. The other way to change the sensor properties is to change the sensor shape itself using auxetic structures that kind of expand in both axes, using voids, bumps, pyramids. One of my favorites is Shar-Pei dog wrinkles. So lots of really exciting applications to change the sensitivity and the selectivity of these sensors. So some recent investigations in my lab include making origami pattern sensors where we're able to tune the sensitivity By about a factor of 2, we're digging more into that behavior now, as well as making morphable and reconfigurable sensors that are tuned through applying a current that melts a material so it's temperature reconfigurable. Okay, that was a lot of information about soft sensors in a very short amount of time. I wanted to convey here that I'm really excited about the promise for a wide range of applications that soft sensors hold. I think that engineering the structure is one key to fulfilling that promise. And I work a lot on sensors. I'm really interested in particular applications. So in particular, if you're working in wearables, machine learning related to wearables, other areas of robotics, if you want to study motion in any particular ways, if you have zany ideas how to use a soft sensor, please let me know. My email is at the bottom there. I am at Northeastern University in the ECE department. Thank you so much.